This is one of the most highly anticipated topics ever covered on Infinity Beyond. Whether you directly asked for it or just followed the enormous buzz across the internet, you've probably heard of the James Webb Space Telescope, JWST. The most powerful space observatory humanity has ever launched. Unlike any telescope before it, JWST had to be folded like origami to fit into the launch vehicle. Why? Because when fully deployed, it's about the size of a tennis court. But this enormous marvel is more than just size. It's the eye that peers into the infancy of the universe, all the way to when the very first stars and galaxies were born. At a cost of 10 billion shekels. This is one of the most expensive scientific instruments ever constructed. Why is it so costly? Precision? Power? Complexity. It must operate at near absolute zero temperatures, around 233 degrees C, to ensure that its own heat doesn't interfere with the delicate sensors designed to capture the faintest infrared signals from across the cosmos. Compared to its predecessor, the Hubble Space Telescope, James Webb is not just an upgrade. It's an evolutionary leap. Where Hubble sees mostly invisible and ultraviolet light, Webb observes the universe in infrared, allowing it to see through cosmic dust and reveal galaxies and stars hidden from view. Imagine peeking behind a cosmic curtain and seeing creation in progress. The mirror itself is a technological triumph, made of that beryllium and coated in gold. It's 6.5 meters in diameter, far larger than Hubble's. This size allows Webb to collect more light, giving it the ability to observe objects that are both faint and incredibly distant. But this power comes with a catch. Everything must go right. If a single segment failed to unfold correctly, if one thermal shield ripped, or if the instruments didn't calibrate, the entire mission would be jeopardized. That's why NASA, ES, and CSA scientists spent over 25 years designing, testing, and validating every mechanism. Webb launched aboard an Ariane 5 rocket on December 25, 2021, from French Guiana. It then spent a month traveling to Lagrange Point 2, a gravitationally stable point 1.5 million kilometers from Earth. This location offers a thermally stable environment and a consistent position behind Earth's shadow, perfect for uninterrupted observation. And then, the miracle unfolded. Literally. Over the course of several nerve-wracking weeks, Webb's sunshield unfurled, its mirror segments aligned, and its instruments powered up. The world held its breath, and one by one, the systems came online flawlessly. We weren't just seeing engineering excellence, we were watching the beginning of a new era in space exploration. Once operational, Webb began capturing images that stunned even the most seasoned scientists. From baby stars being born in stellar nurseries to galaxies formed just a few 100 million years after the Big Bang, Webb has shown us sights we never dreamed we'd witness in our lifetime. But this is only the beginning. Infinity Beyond will explore how Webb is being used to study exoplanets, detect atmospheric signatures, and possibly find the building blocks of life beyond Earth. It may even answer one of the oldest questions in human history. Where did we come from? This isn't just a telescope. It's a time machine, a cosmic archaeologist, and a symbol of what we can achieve when science, collaboration, and ambition unite. Stay tuned, because what comes next might just change everything. James Webb has moved on to explore something just as mysterious and beautiful: planetary nebulas. These ethereal, colorful clouds in space are not planets, despite their name. They're formed from the outer layers of dying stars, blasted into space during their final breaths. It's cosmic recycling at a grand scale, the last will and testament of a star. One of the Webb telescope's superpowers is its unmatched ability to see through cosmic dust. In visible light, these nebulas can look like soft glows or even empty regions. But in infrared, Webb reveals a hidden story: glowing gases, intricate layers of dust, and the fingerprints of elements that may one day form new stars and planets. Take, for example, the image of the Southern Ring Nebula, also known as NGC 3132. Through Webb's instruments, we can clearly observe how material is being pushed outward, forming beautifully chaotic structures. More than just a pretty picture, this view tells us about the raw chemical composition of the expelled material. Hydrogen, carbon, oxygen, the very elements that make up planets and even life itself. But there's a twist. When scientists compared Webb's image to that of Hubble, they noticed something peculiar. The second star in this binary system, long thought to have gone supernova, was actually still intact. It hadn't exploded yet. Webb allowed astronomers to track the fine movement and gravitational interplay between the two stars, revealing how their orbits stir the nebula, creating swirls, knots, and filaments of matter. This is crucial because it gives us a real-time lab to study how star systems evolve, interact, and eventually die. And the dust that emerges, it may one day collapse into entirely new stars and solar systems. The death of one generation becomes the seed for the next. This cycle of stellar death and rebirth is the rhythm of our galaxy, and Webb is now watching it unfold in stunning detail. But Webb isn't just gazing inward. Its gaze extends far on beyond our galaxy, to places where new stars are forming even now. In star-forming regions like the Carina Nebula, Webb peels back the dust veils and uncovers protostars in their infancy, some just a few thousand years old. You're literally looking at suns being born, hundreds or even thousands of light years away. Imagine this: the light captured in Webb's images began its journey long before humans invented telescopes, even before the pyramids were built. That ancient light has traveled across time and space, only to be caught by Webb's golden mirrors, a moment billions of years in the making. And it's not just about observing, it's about learning how stars form, what materials are involved, and under what conditions planets might form around them. Webb gives us the ability to trace our cosmic origins, atom by atom, light wave by light wave. Every image Webb captures is not just a view, it's data. Precise information about temperature, chemical content, density, movement. Scientists can now map star nurseries and dying stellar shells with mathematical precision. We can simulate how matter clumps, cools, and collapses into new celestial bodies. It's as if Webb handed humanity a key to the universe's deepest vaults. And perhaps the most astonishing thing? We're still just scratching the surface. Infinity Beyond will continue exploring what these observations mean, not just for astronomers, but for everyone who's ever looked up at the night sky and wondered, what's out there? Webb isn't just changing astronomy. It's changing how we think about life, death, and rebirth on a cosmic scale. From the final sigh of a dying star to the spark of newborn suns, we are now watching the eternal dance of creation unfold in high definition. So buckle up. The next images might just rewrite our understanding of the universe once again. The James Webb Space Telescope isn't just designed to look at dying stars or stellar nurseries. One of its most hotly anticipated missions is to investigate exoplanets, distant worlds orbiting stars outside our solar system, in search of atmospheres that might support life. This is a game changer. For the first time in history, we now have a tool capable of analyzing the chemical makeup of alien atmospheres. By studying how a planet's atmosphere filters the light of its star, Webb can detect elements like water vapor, methane, carbon dioxide, and even ozone, potential markers of biological processes. Imagine what it would mean to detect an Earth-like planet with a breathable atmosphere. That wouldn't just be a scientific milestone. It would redefine humanity's place in the cosmos. But Webb's power doesn't stop there. It is also revealing the secrets of us young galaxies that formed shortly after the Big Bang. These ancient light sources, invisible to most telescopes, are now within our grasp thanks to Webb's infrared sensitivity and massive mirror. When we observe these early galaxies, we're literally looking back in time, more than 13 billion years. What do they tell us? That the early universe was far more chaotic, structured, and surprising than we expected. Galaxies were forming earlier and faster, with more mass and complexity than any previous model had predicted. This challenges long-held assumptions in cosmology and forces scientists to rethink the timeline of galactic evolution. Now take a moment to picture this. You step outside at night and look up at the sky. You see stars, constellations, maybe a planet or two. But what you're seeing, as vast and beautiful as it seems, is just a fraction of what's out there. Light pollution. Atmospheric distortion and the limits of human eyesight prevent us from seeing the true majesty of space. Thankfully, tools like the Hubble Space Telescope gave us the first taste of what lies beyond. Orbiting at around 550 kilometers above Earth, Hubble showed us vibrant nebulae, massive star clusters, and the deep field views that became icons of astronomy. It changed our understanding of astrophysics, revolutionized cosmology, and inspired a new generation of stargazers. But now, Webb takes us deeper. Not just in terms of distance, but in clarity, depth, and meaning. Where Hubble left off, Webb begins, able to see the faintest glimmers of the first light in the cosmos. Webb doesn't just show us images, it delivers data-rich windows into the physics of the universe. It enables us to ask bigger questions and actually start answering them. Where did the first galaxies come from? How do they evolve? Why are some galaxies spiral while others are elliptical? Are black holes essential to galaxy formation? What happens to matter at the edges of time and gravity? Every new image, every data set brings us closer to answers. And even more exciting, to questions we haven't even thought of yet. With each revelation, Webb not only brings distant objects into focus, but brings ourselves into sharper clarity. We begin to understand that we are part of a vast, ever-changing, interconnected universe that has been unfolding for billions of years, and will continue long after we're gone. That perspective is both humbling and empowering. It challenges us to look beyond borders, beyond conflicts, and beyond the narrow focus of daily life. Because when you're looking across 1.5 billion years of history, everything else seems small. And yet, despite the scale, it is precisely this cosmic perspective that reminds us of how special life is, how rare it might be, and how important it is to cherish our fragile world. Infinity Beyond invites you to join this journey not just as a viewer, but as a fellow explorer. Together, we'll uncover the universe's greatest mysteries, and perhaps redefine what it means to be human. Among the many strange and wondrous discoveries the James Webb Space Telescope is helping us understand, few are as enigmatic as the topic of dark matter, that invisible substance that binds galaxies together, yet refuses to reveal itself directly. In one stunning image, Webb captured a ghostly galaxy, unlike anything we had seen before. Behind it, you can spot distant galaxies stretching into the depths of space. But something about this galaxy stood out. It appears to be missing all of its dark matter. Yes, a galaxy without dark matter. This defies everything we thought we knew about galaxy formation. Normally, dark matter provides the gravitational scaffolding that helps galaxies form and maintain structure. But this mysterious object seems to hold itself together through visible matter alone. This discovery wasn't just surprising, it was revolutionary, and it raises more questions than answers. Why is it missing dark matter? Did it lose it somehow? Did it form differently? Or does it suggest that our entire model of dark matter needs revision? Webb's ability to observe with unprecedented clarity allows astronomers to study this galaxy in detail, measuring star velocities, gravitational lensing effects, and intergalactic interactions. Every data point brings us closer to understanding what dark matter is, or isn't. Now let's travel even further. Over 300 million light-years from Earth lies the Coma Cluster, a massive congregation of over 1,000 galaxies, all held together by gravity. It was one of the first regions in space where scientists detected the gravitational effects of dark matter, the unseen force keeping everything from flying apart. In the breathtaking images of the Coma Cluster, you can spot intra-cluster globular clusters, spherical groups of stars floating between galaxies, bound not to any single galaxy, but to the gravity of the cluster as a whole. It's a vision of chaos and order, a gravitational dance spanning millions of light-years. But Webb isn't done surprising us yet. Let's venture even deeper, over 9 billion light-years away, to gaze at a star named Icarus, officially designated as MX J149 lensed star 1. For a time, this was the most distant star ever detected. Its light has taken over 9 billion years to reach us. Think about that. This tiny pinpoint of light we now see in a Webb image began its journey before our solar system even existed. So how can we even see such a faint, distant star? Thanks to a cosmic trick called gravitational lensing. A massive galaxy cluster sits between Earth and Icarus, and its immense gravity bends space-time like a magnifying glass, amplifying the light of the distant star and sending it our way. Without that natural lens, Icarus would be far too faint for even Webb to detect. But now that we can see it, scientists can study not just the star itself, but the properties of the lensing galaxy cluster, including the distribution of dark matter within it. Every discovery builds on another. By tracing distant light, we uncover nearby mysteries. By studying the strange, we begin to understand the familiar. It's all part of a cosmic tapestry, interconnected, layered, and more beautiful than we ever imagined. The James Webb Space Telescope doesn't just show us stars and galaxies. It helps us uncover the invisible, map the mysterious, and ask questions we never thought to ask. Is dark matter a substance? A field? An error in our understanding of gravity? These are no longer philosophical questions. They are data-driven investigations powered by the most advanced telescope ever created. As we continue our journey, Infinity Beyond will explore the boldest theories, the wildest predictions, and the most awe-inspiring images from Webb's mission. Because out there, in the cold silence of the void, the universe is whispering its secrets. And now, at last, we can hear them. Long before the James Webb Space Telescope began unveiling galaxies at the edge of time, astronomers were already intrigued by something mysterious lurking much closer, at the farthest edges of our own solar system. For decades, Pluto was considered an oddball. Its eccentric orbit and small size puzzled scientists. But then came a revolutionary idea. What if Pluto wasn't alone? What if it was just one of many distant icy objects beyond Neptune? In 1951, astronomer Gerard Kuiper theorized the existence of a belt of icy bodies, remnants from the solar system's formation, just beyond Neptune's orbit. But at the time, telescopes weren't powerful enough to detect them. The idea remained speculative for nearly half a century. Everything changed in April 1992, when astronomers David Jewett and Jane Liu discovered 1992 QB1, the first confirmed Kuiper Belt object, or KBO. Although Pluto was discovered way back in 1930 and its largest moon, Charon, in 1978, neither was confirmed to be part of a larger population until 1992 QB1 blew the doors wide open. Since then, astronomers have discovered thousands of KBOs, populating a region now known as the Kuiper Belt, a vast donut-shaped zone stretching from about 30 to 55 AU astronomical units from the Sun. That's 30 to 55 times the distance between Earth and the Sun. Let's imagine embarking on a journey from the Sun, moving past the terrestrial planets, Mercury, Venus, Earth, Mars, then crossing the gas giants, Jupiter and Saturn, continuing through Uranus and Neptune. As we cross Neptune's orbit, we enter a realm of shadows and ice, the Kuiper Belt. Here, time seems to stand still. These objects are ancient, untouched, and frozen in time. They're the leftovers from the early solar system, never coalesced into planets, but still holding secrets about the origins of everything. Some of the KBOs are spherical and large enough to be considered dwarf planets, including Eris, Haumea, and Makemake, all discovered after Pluto, and some even larger. In fact, it was the discovery of Eris in 2005, a KBO nearly the same size as Pluto, that forced the astronomical community to redefine what a planet is. The result? Pluto was demoted to dwarf planet status in 2006, joining its icy siblings in the Kuiper Belt. While this decision stirred public debate, it actually represented a leap forward in our understanding of planetary classification. It forced scientists to acknowledge that the solar system is far more complex than a simple 9-planet model. But what's more exciting is what we don't know about the Kuiper Belt. Are there massive undiscovered objects lurking beyond? Could there be a Planet 9 hiding in the darkness, perturbing the orbits of smaller KBOs? Webb's high-resolution infrared capabilities could one day help confirm or refute these hypotheses. Its sensitivity to cold, distant objects gives astronomers a better chance of detecting faint light from hidden worlds far beyond Neptune. But even now, missions like NASA's New Horizons, which flew past Pluto in 2015, are helping to map and understand the Kuiper Belt up close. After its Pluto flyby, New Horizons went on to visit Arrokoth, a contact binary KBO, revealing never-before-seen data about the building blocks of planets. These ancient objects are more than space debris. They are time capsules, icy archives that preserve the chemical conditions of the solar system's birth. Understanding the Kuiper Belt could reveal how planets formed, how Earth got its water, and even how life may have emerged. In the next chapters, Infinity Beyond, we'll guide you deeper into this icy wilderness, where dwarf planets drift in silence, where gravitational forces dance in slow motion, and where every rock of ice could hold clues to our very existence. So fasten your seatbelt, because the edge of the solar system is only the beginning. Not all Kuiper Belt objects stay in their icy, distant orbits. Sometimes a collision or the gravitational pull of Neptune can knock one off course, sending it spiraling inward toward the Sun. When that happens, the object becomes a short-period comet, an icy traveler that loops around the Sun every few decades or centuries. These comets, often with orbital periods under 200 years, are some of the most captivating sights in the sky. As they approach the Sun, its heat begins to vaporize the comet's surface, releasing gases and dust in long, glowing tails. These brilliant displays are what we see from Earth, celestial fireworks, trailing across the night sky. One of the most iconic of these is Halley's Comet, which has a period of about 76 Earth years. Its recorded appearances go back to ancient times, tracked by Chinese, Babylonian, and European astronomers alike. Another famous visitor is Comet Shoemaker-Levy 9. But unlike most comets, it didn't just pass by. It crashed into Jupiter in 1994, producing the first direct observation of two celestial bodies colliding in our solar system. The impact was spectacular. Pieces of the comet slammed into Jupiter's atmosphere, creating fireballs the size of Earth. Dark scars lingered on the gas giant's surface for months, visible even through amateur telescopes. It was a sobering reminder of the raw, kinetic energy that exists in our cosmic neighborhood. And while Jupiter survived, the event highlighted something critical. Cometary impacts aren't rare. They're part of the natural evolution of solar systems. Some comets come from the Kuiper Belt. Others may originate in the Kuiper-scattered disk, a chaotic outer region beyond the belt. And beyond that, still further out, lies the Oort cloud, a hypothetical shell of icy objects thought to be the source of long-period comets, those with orbits spanning thousands or even millions of years. These icy time capsules are more than just pretty trails of dust and gas. They're all rich in organic molecules, frozen since the birth of the solar system. By studying comets, we may uncover clues about the origins of water on Earth, and even the building blocks of life. But while some comets pass harmlessly by, others raise alarms. Recently, astronomers have tracked near-Earth objects, NEOs, asteroids or comets whose orbits bring them within close range of our planet. One such object, named 2024 Y4, made headlines due to its sudden brightening, which at first suggested it might become the next great naked-eye comet. But then, it disintegrated. Like many fragile visitors from the outer solar system, its icy nucleus fractured before it could make a spectacular show. Still, these events remind us of the importance of monitoring the skies, not just for beauty, but for safety. The James Webb Space Telescope plays a surprising role here too. While it's optimized for distant galaxies, Webb's infrared sensors are incredibly sensitive and can detect faint heat signatures from comets, asteroids, and even interstellar objects passing through the solar system. Combined with ground-based telescopes and sky surveys, Webb helps provide a three-dimensional view of cometary dynamics. Where they are, what they're made of, and how they're changing over time. We now know that comet tails aren't always alike. Some comets produce twin tails, one of gas, the other of dust. Others develop ion tails that react to the solar wind and magnetic fields, stretching for millions of kilometers. Each comet is like a unique signature, a wandering relic from the dawn of time. And just as they come, they go, sometimes silently, sometimes with a flash of brilliance, but always they leave behind wonder and questions. What lies in the vast reaches beyond the Kuiper Belt? How many more icy visitors are waiting to enter our skies? Could a future comet pose a real danger to Earth? Or could it one day bring us answers about life beyond? At Infinity Beyond, we explore these questions not to frighten, but to understand, to appreciate our fragile place in a dynamic and sometimes unpredictable cosmos. So next time you see a streak of light across the night sky, remember, it might be more than just a shooting star. It could be a messenger from the frozen edge of our solar system, a ghost of formation, lighting up the sky in farewell. Stay curious, because the universe is always sending signals, and now with tools like Webb, we're finally starting to receive them. Imagine skipping a stone across a pond, that satisfying moment when it touches the surface at just the right angle and glides forward before sinking. Now apply that concept to Pluto. Yes, the dwarf planet at the edge of our solar system. Scientists believe that one of Pluto's most striking features, the heart-shaped region, known as Hautamba Regio, was formed by a similar event, a low-velocity, oblique impact. Imagine a cosmic water balloon hitting Pluto at an angle, not directly, leaving behind an elongated depression, a kind of icy splat across the surface. This wasn't just a collision, it was a sculptor's touch, shaping Pluto's geology in a way we're only beginning to understand. These insights come to us thanks to NASA's New Horizons mission, which gave humanity its first ever close-up look at Pluto in 2015. Before that flyby, Pluto was just a blurry dot in telescopes. Afterwards, it became a richly textured world, with mountains, ice plains, and a vibrant atmosphere of nitrogen and methane. But Pluto isn't alone. Its largest moon, Charon, proved to be just as surprising. One of the most astonishing features on Charon is a vast equatorial tectonic belt, a system of cracks and canyons so large that they span a significant portion of the moon's surface. What caused them? Evidence suggests that Charon once harbored a subsurface ocean, rich in liquid water beneath an icy crust. As that ocean slowly froze over time, it expanded, causing the surface to crack and split, like a bursting frozen pipe. Think about that. An ancient water world, orbiting a distant dwarf planet, may have once had the conditions necessary for a life, at least microbial life. Every discovery we make in the Kuiper Belt continues to challenge our assumptions. Far from being a static, frozen graveyard of planetary leftovers, this region is dynamic, complex, and full of stories, waiting to be uncovered. So what comes next? New Horizons is still active and is expected to exit the Kuiper Belt sometime between 2028 and 2029. While it has no confirmed next target, there is hope that NASA, with help from powerful observatories like the James Webb Space Telescope, may identify another flyby candidate before then. Such a target could offer us one more historic encounter. Before New Horizons drifts into interstellar space, a final goodbye before it joins Voyager on its silent journey into the unknown. But even if it never sees another object up close, its legacy is secure. The data it returned on Pluto and Charon alone is enough to rewrite textbooks and reshape how we view small, icy bodies. And more importantly, it has inspired a generation of scientists and dreamers. Meanwhile, the James Webb Space Telescope continues its work, peering deep into regions that New Horizons could never reach. Webb's infrared vision allows it to study the surfaces, atmospheres, and thermal signatures of distant Kuiper Belt objects, helping scientists narrow down where to look for future missions. What we've learned is this: even the most remote, seemingly lifeless corners of our solar system are brimming with geological activity, chemical processes, and hidden histories. Maybe, just maybe, the ingredients for life are not rare exceptions, but common threads woven throughout the cosmos. At Infinity Beyond, we believe these discoveries matter not just for science, but for humanity. They tell us that we are part of a vast, evolving system, a story still being written, with new chapters unfolding at the frozen edge of sunlight. The Kuiper Belt, once thought to be the solar system's end, might actually be on the beginning of something far greater. Long before James Webb peered into the early universe, another mission, smaller, slower, but no less ambitious, set out to explore our solar system. Voyager. Launched in 1977, the Voyager spacecraft were built during a rare cosmic alignment, an event that occurs only once every 176 years. This alignment allowed a spacecraft to use gravity assists from all four outer planets, Jupiter, Saturn, Uranus, and Neptune, to slingshot from one to the next with the minimal fuel. This concept of gravity assist was relatively new at the time. It had been tested on earlier Pioneer missions, but never on this scale. The potential was enormous, a grand tour of the outer planets. But there was a catch. NASA had a narrow window to launch before the alignment closed. And worse, there wasn't enough time or political will to fund a full-fledged grand tour mission. Congress was hesitant, budgets were tight, and timelines were aggressive. So the Voyager teams made a bold decision. They built two spacecraft, Voyager 1 and Voyager 2, equipped them with 11 scientific instruments, and designed them with flexibility in mind. These spacecraft weren't just for short trips. They were built for endurance, equipped with redundancies in critical systems, including instruments that could be turned off or on as needed to conserve power. It was an engineering gamble, but it paid off. Voyager 2 was launched first on August 20, 1977, followed by Voyager 1 on September 5. Despite its later launch, Voyager 1 took a faster trajectory and overtook its sibling, and the rest is history. The spacecraft visited Jupiter and Saturn, sending back breathtaking images and revealing features never seen before. Jupiter's raging Great Red Spot, Saturn's majestic rings, and moons like Io, Europa, and Titan, which would later become prime targets in the search for extraterrestrial life. Voyager 2 continued its journey, becoming the only spacecraft to ever visit Uranus and Neptune. It revealed Uranus's tilted magnetic field and Neptune's deep blue atmosphere, filled with supersonic winds and storm systems. Each planetary encounter was like a space documentary unfolding in real time. And back on Earth, scientists and citizens alike were captivated. But the story didn't end there. After their planetary flybys, both Voyagers continued outward and entered the final phase of their mission, the Voyager Interstellar Mission. In just 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind is no longer strong enough to push against interstellar space. It became the first human-made object to enter interstellar space. Voyager 2 followed in 2018, confirming the data and validating one of the most extraordinary achievements in the history of exploration. And yet they're still talking to us. Despite being nearly 20 billion kilometers away, both Voyagers continue to send back data, using their plutonium-powered RTGZU and ancient yet reliable communication systems. Each byte of data that reaches Earth takes more than 20 hours to arrive, traveling at the speed of light across the vast silence of space. And what's even more poetic, each Voyager carries a golden record, a phonograph disc encoded with sounds and images of Earth, greetings in dozens of languages, and even music from Bach, Beethoven, and Chuck Berry. These records are meant as a message to any intelligent life that might someday find them. It's a time capsule of humanity, floating among the stars. The Voyagers are not just missions. They are old legends, monuments to human curiosity, perseverance, and ingenuity. And while James Webb looks outward into the cosmic past, Voyager looks back at us, slowly fading into the night, yet never forgotten. Infinity Beyond celebrates these twin spacecraft, not only for what they discovered, but for what they represent: the spirit of exploration. The idea that even with limited tools, uncertain funding, and outdated technology, we can achieve the extraordinary. Because sometimes all it takes is a well-timed launch and an unshakable belief in the journey ahead. There's something hauntingly powerful about seeing our home, Earth, from an unimaginable distance. One such image was captured by the Apollo 11 crew from the Moon, but another would soon rival it in emotion and scale. A photo taken by Voyager. Far beyond the Moon's orbit, where Earth appears as a tiny blue marble, floating beside the Moon in the dark sea of space. It's a perspective that strips away borders, politics, and divisions, and reminds us how precious and fragile our world truly is. But Voyager's journey was far from over. After its launch in 1977, Voyager 1 spent nearly 2 years cruising through the cold void before finally approaching its first major target, Jupiter. Jupiter is no neighbor. It's approximately 714 million kilometers, or 444 million miles, from Earth. But thanks to its optimized trajectory and faster speed, Voyager 1, traveling at 17 kilometers per second, reached Jupiter before its twin, Voyager 2, even though it launched later. On March 5, 1979, Voyager 1 made its historic flyby. This wasn't the first spacecraft to visit Jupiter. That honor goes to Pioneer 10, which passed by in 1973. However, Voyager 1 brought something Pioneer never could: unparalleled image quality, comprehensive instruments, and unforgettable discoveries. Through Voyager's eyes, the gas giant transformed from a blurry sphere into a dynamic, violent world, filled with roaring storms, bands of swirling clouds, and most notably, the Great Red Spot. This iconic storm, larger than Earth, had been observed for centuries, but Voyager showed it in unprecedented detail, capturing its massive rotating cloud formations and revealing that it's a complex weather system, not just a surface marking. But the real surprises came from Jupiter's moons. Until that point, most scientists believed the moons of Jupiter were cold, geologically dead bodies. Voyager 1 proved them wrong. It flew past Ios, Jupiter's innermost Galilean moon, and revealed a volcanic hellscape, the most geologically active body in the solar system. Volcanoes were erupting, spewing sulfur hundreds of kilometers into space. No one expected this. Io was alive. Then came Europa, a small, smooth, icy moon that appeared strangely free of impact craters. This suggested something beneath the surface, something dynamic. Voyager's data hinted at the possibility of a subsurface ocean, liquid water beneath a crust of ice. These observations would later inspire decades of research and missions, including the upcoming Europa Clipper, designed to explore whether Europa could harbor life beneath its frozen exterior. Voyager also observed Ganymede and Callisto, the two largest Galilean moons, offering new insights into their geology, magnetic fields, and surface compositions. And let's not forget Jupiter's ring system. Yes, it has one. While not as prominent as Saturn's, Voyager was the first to discover and image the thin, dusty rings surrounding the gas giant. With all this data, Voyager 1 reshaped our understanding of gas giants and their moons. It showed that the outer solar system was not a frozen, dead wasteland. It was active, diverse, and full of surprises. Meanwhile, Voyager 2 would follow a few months later, on July 9, 1979, taking a slightly different path and offering complementary data. This twin spacecraft confirmed many of Voyager 1's findings while preparing for its own extended journey to Uranus and Neptune. Back on Earth, people were captivated. These were not just scientific breakthroughs, they were new worlds revealed. For the first time, humanity saw Jupiter up close, with all its complexity and beauty. And all the while, Earth was getting smaller in the rearview mirror. Voyager's photo of Earth and the Moon from deep space wasn't just a postcard, it was a perspective-shifting moment. It reminded us that in the vast darkness of space, our planet is a fragile oasis, the only known harbor of life. Infinity Beyond believes these moments matter, not just for scientists, but for everyone. They show us what's possible when curiosity meets technology, when ambition reaches beyond what's visible, and when we dare to send our machines and our dreams where no one has gone before. As we continue this journey with Voyager, remember, every distant planet we pass, every moon we photograph, and every pixel of data we receive is a testament to human potential. And this was only Jupiter, the first stop. After its historic encounter with Jupiter, Voyager set its sights on the next celestial marvel, the majestic Saturn, Lord of the Rings. When Voyager reached Saturn in 1980, Voyager 1, and 1981, Voyager 2, it sent back images that were not just beautiful, but also deeply mysterious. The iconic rings, once thought to be smooth, uniform structures, were revealed to be incredibly complex, dynamic, and even a bit chaotic. One of the most exciting discoveries was the identification of two small shepherd moons, Prometheus and Pandora, orbiting just inside and outside the narrow F-ring. These moons were critical in confirming a theory that had long been debated, that shepherd moons exist to herd ring material, keeping the particles tightly bound and preventing them from drifting. Think of them as cosmic gatekeepers, gravitational caretakers holding Saturn's delicate rings in place. But Voyager didn't stop at just photographing moons. It also uncovered ghostly features within Saturn's B ring, which completely stunned scientists. These features looked like spokes in a wheel, dark radial markings that moved, shifted, and even vanished between images. At first, these spokes were thought to be errors, glitches in the data. But repeated sightings confirmed they were real. And more than that, they didn't behave in any way that fit the existing gravitational models. These mysterious spokes defied traditional orbital mechanics. So, what could cause them? The leading theory involves electrostatic repulsion. As Saturn spins, it generates a strong magnetic field. That field could interact with the smallest particles of dust in the rings, lifting them slightly above the ring plane and creating these shadowy, floating structures. But even today, decades later, the full explanation remains elusive. And that's what makes it exciting. Even in one of the most studied planetary systems, there are still mysteries waiting to be solved. Saturn also revealed some of the most diverse and fascinating moons in the solar system. Voyager imaged Titan, Saturn's largest moon, which was cloaked in a dense orange atmosphere, thicker than Earth's. The data hinted at hydrocarbon clouds and possible liquid methane lakes, making Titan a top candidate in the search for alien environments. It also passed by Mimas, the so-called Death Star moon, due to a massive impact crater that gives it an uncanny resemblance to a certain sci-fi space station. Enceladus, another icy moon of Saturn, showed surface features that hinted at internal heating, leading scientists to later discover geysers of water vapor and a hidden subsurface ocean, another potential cradle for microbial life. And let's not forget the ring system itself. Voyager's close-ups revealed that Saturn's rings are made up of countless individual particles, ranging in size from micrometers to meters, each orbiting Saturn like miniature moons. What we thought was a flat disk turned out to be a dizzying ballet of frozen fragments, constantly shifting, colliding, and regrouping. Voyager taught us that Saturn is not just a planet, it's an ecosystem, a delicate interwoven system of rings, moons, magnetism, and motion. And though Voyager was only meant to fly by, its data opened the door for deeper missions like Cassini, which orbited Saturn for over 13 years and expanded upon Voyager's legacy. But Voyager will always be the first. The Pathfinder, the mission that revealed Saturn's rings in full glory and left scientists scratching their heads at phenomena like the mysterious spokes. It reminds us that science is not about having all the answers. It's about being open to wonder, to encountering something that breaks your model, and instead of dismissing it, saying, "Let's figure it out." Here at Infinity Beyond, we honor Voyager's discoveries not just for what they revealed, but for what they still challenge us to understand. Saturn, with its beauty and its enigmas, remains one of the most compelling chapters in Voyager's journey and in humanity's cosmic story. So as Voyager drifts ever farther from the Sun, carrying our hopes and questions with it, Saturn lingers behind, shining, spinning, and still whispering secrets through the spokes of its shimmering rings. After unveiling the grandeur of Jupiter and the mystery of Saturn, Voyager 2 ventured even farther into the cold, blue unknown, toward the seventh planet from the Sun, Uranus. Voyager 2's flyby of Uranus on January 24, 1986 was, and remains, the only time a spacecraft has visited this planet up close. What it discovered left scientists fascinated and, in some ways, perplexed. Uranus is a strange world. It rotates on its side, with an axial tilt of 98 degrees, essentially rolling around the Sun like a ball. This tilt likely resulted from a massive collision in the distant past, a planet-sized impact that knocked it off its original axis. But it's not just the planet that's strange, it's where moons are equally bizarre. At the time of Voyager's encounter, 5 main moons were known: Oberon, Umbriel, Titania, Ariel, and Miranda. Since then, the total number of known Uranian moons has grown to 27. But these 5, the OGs, remain the most studied. Let's start with the outermost. Oberon. Covered in craters and dark material, it appears to be a relic from the solar system's early days. Voyager's images showed little sign of recent geological activity. Its surface is ancient and untouched. Close to Oberon is Umbriel, equally dark and heavily cratered. Both moons are believed to be wild ice rock conglomerates, similar to Saturn's moons, with surfaces coated in frozen methane, ammonia, and water ice. But things get more interesting as we move inward. Titania, the largest of Uranus's moons, shows evidence of huge fault systems and canyons, signs that some internal activity may have taken place in the distant past. Its surface is slightly brighter, hinting at tectonic or thermal processes that may have shaped its landscape. Even more striking is Ariel. Voyager captured an image of Ariel from just 229,000 kilometers away, revealing a bright surface with long, deep valleys and flow-like features. This suggests that Ariel may have once been geologically active, with icy lava flows reshaping its terrain. And then there's Miranda. Voyager's flyby of Miranda was one of the mission's most surprising moments. This tiny moon, only about 500 kilometers in diameter, turned out to be one of the strangest objects in the solar system. Miranda's surface is a patchwork of cliffs, canyons, ridges, and strange oval-shaped regions, called coronae. It looks as if the moon was shattered and reassembled, piece by piece, like a cosmic jigsaw puzzle. One of the most dramatic features is Ca Verona Rupus, a cliff estimated to be 120 kilometers, 12 miles high. possibly the tallest known cliff in the solar system. If you were to fall from the top, it would take over 10 minutes to reach the bottom, assuming Uranus's low gravity didn't slow you even further. But how did Miranda become so fractured? Scientists believe it may have experienced multiple violent events, possibly tidal forces from Uranus, or a series of impacts and refreezing cycles that reshaped its core and crust. Or perhaps, just perhaps, Miranda was once geologically alive, with internal heat creating upwellings of material that cracked the surface open. Voyager gave us just a brief look, but that look opened countless questions. Beyond the moons, Voyager also studied Uranus's faint ring system, a discovery made just a few years earlier from Earth. Voyager confirmed the existence of 13 rings, narrow and dark, orbiting the planet like delicate brushstrokes. Unlike Saturn's brilliant rings, Uranus's are almost invisible, made of our microscopic dust and ice, possibly the remains of shattered moons or asteroids that wandered too close. The planet itself, while seemingly featureless in visible light, held surprises too. Voyager detected wind speeds of over 900 km/h and a powerful magnetic field, tilted and offset from the planet's core, adding to its already strange character. It also measured the planet's atmosphere, composed mainly of hydrogen, helium, and methane, the latter giving Uranus its pale cyan blue color. Though Voyager 2 spent only a few days near Uranus, the data it sent back revolutionized our understanding of the ice giants. And perhaps more importantly, it reminded us that even in the darkest, coldest corners of the solar system, where sunlight is faint and heat is nearly absent, there is still complexity, beauty, and mystery. At Infinity Beyond, we believe that Miranda's fractured surface and Ariel's bright plains are as deserving of awe as Saturn's rings or Jupiter's storms, because the farther we go, the more we realize there's no such thing as ordinary in space, only places we haven't seen yet. And Voyager? It saw them first. As Voyager left the planets behind, it continued drifting farther from the sun, toward the vast unknown. And with every passing year, it became less of a planetary mission and more of a cosmic messenger. One photo, in particular, encapsulated this transition: the pale blue dot. Captured in 1990 by Voyager 1 at the request of Carl Sagan, this iconic image shows Earth as a tiny speck suspended in a beam of sunlight, taken from 6 billion kilometers away. In Sagan's words, it reminds us to cherish the pale blue dot, the only home we've ever known. Even today, decades later, this image resonates with awe, humility, and responsibility. It's not just a photograph, it's a reminder of how small we are and how much farther we still have to go. But the mission wasn't over. In 1981, Voyager 1 veered about 35 degrees north of the ecliptic, the plane on which most planets orbit. Voyager 2 went 148 degrees south. These divergent paths sent them on separate trajectories toward the outermost edge of the heliosphere, the vast bubble carved out by the sun's influence. Their next challenge? To cross into interstellar space, a journey that would take decades. Before they could reach the stars, the Voyagers had to pass through the termination shock, where the sun's supersonic solar wind slows down dramatically as it begins to encounter the resistance of the interstellar medium. Beyond the termination shock lies the Helios Heath, a turbulent region where solar particles pile up, becoming hotter and denser. It's the cosmic equivalent of a ship battling stormy seas at the edge of port. Finally comes the heliopause, the invisible boundary where the solar wind stops entirely and the pressure from the interstellar wind takes over. This is the true frontier. Beyond it lies Interstellar space. In 2012, Voyager 1 crossed the heliopause, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, confirming measurements and showing that the boundary was not smooth or symmetrical, but instead fluctuates like the tides of an invisible ocean. Now, drifting through this alien realm, the Voyagers continue to send back data about cosmic rays and magnetic fields and plasma waves. They are our only eyes and ears in a region untouched by the sun. And yet, even now, decades later, they still speak to us. Their power comes from plutonium-based radioisotope thermoelectric generators, RTGs. Over time, their power is fading. Some instruments have already been shut down to conserve energy. Eventually, communication will cease, not because they broke, but because the universe is simply too vast. But their legacy will continue. Each Voyager carries a golden record, a time capsule of Earth. It contains 115 images, recordings of music and natural sounds, and greetings in 55 languages. It was designed for one purpose: to say, this is who we are. Will it ever be found? Maybe not. But that's not the point. The golden record is a message of hope, a declaration that we existed, that we were curious, and that we reached for the stars. At Infinity Beyond, we believe the Voyagers are not just spacecraft. They are high symbols of human perseverance. They show what's possible when science and imagination work together. They remind us that even the most fragile machines, built in the analog age, can surpass expectations and travel farther than any dreamer dared imagine. So where are they now? Voyager 1 is over 24 billion kilometers away, traveling at over 60,000 kilometers per hour. Voyager 2 trails slightly behind, still exploring a different path through interstellar space. They will continue drifting through the galaxy for millions of years, long after the Earth is changed, long after we're gone. And yet, out there in the void, they carry a tiny piece of us, our music, our greetings, our essence. In the end, Voyager is a love letter, a message from a small blue planet that once dared to explore. From the surface of Earth to the edge of forever, that is the legacy of Voyager. And for as long as we listen, the stars will whisper back. What? Imagine this. You're an engineer at NASA's Deep Space Network. You're sitting at your workstation, monitoring the health of Voyager 1, the most distant human-made object in the universe. A routine transmission has just arrived, except something's wrong. The data doesn't make sense. Instead of the expected numbers, coordinates, thruster status, temperature readings, you see strings of zeros, strange, 377s, and nonsensical values. Voyager seems to be reporting that it's doing things it physically cannot do. Is it turning in the wrong direction? Is it spinning? Is it malfunctioning? But here's the strange part. Is still receiving a clean signal. It's strong, stable, and coming from the right direction. If Voyager were actually turned away, the signal would be weak or missing altogether. Yet everything seems fine on the surface, except for the old garbled telemetry. Welcome to the bizarre world of deep space troubleshooting. You see, every command sent to Voyager and every bit of data received takes over 22 hours to travel one way. That's 44 hours round trip. It's like trying to have a conversation with someone across those light days, not light seconds. It's no longer texting. It's like sending letters by bottle across a cosmic ocean. In this scenario, NASA's engineers suspected that Voyager's attitude articulation and control system, AACS, which tells the spacecraft where it is pointed, was feeding data to the wrong memory location. That means Voyager wasn't actually turning. It was just misreporting what it thought it was doing. Even more importantly, the antenna was still pointed perfectly at Earth, or we wouldn't be receiving anything. But how do you fix a spacecraft? Launched in 1977, built with computers less powerful than a modern calculator, and running software written in languages most current engineers have never used, very carefully. Teams at NASA began replicating the problem, using ancient codebooks, schematics, and simulated models of the spacecraft's behavior. Every command had to be planned with surgical precision, because a single mistake could permanently silence Voyager. Eventually, they traced the issue. A corrupted bit of software was telling the AACS to store orientation data in the wrong place. Fortunately, they were able to reroute the data, bypass the faulty code, and restore Voyager's ability to report accurate information. Problem solved, for now. But the deeper truth is this: Voyager is getting old. Its power is dwindling. Its components are decades past their expected lifespan. And yet, like a wise elder, it still whispers across the stars, one packet at a time. These kinds of glitches are becoming more frequent, more unpredictable. The engineers know that someday soon there will be a final message, one last signal before Voyager goes silent forever. But until that day, they will keep listening, because every byte from Voyager is precious, not just as science, but as a symbol of what we can achieve when we dare to reach beyond. Here at Infinity Beyond, we see this moment not as a failure, but as a testament. Even when the spacecraft speaks in code, even when the software hiccups and memory glitches, the human spirit of problem-solving endures. Voyager may be alone out there, but it is not forgotten. It still carries our dreams, our knowledge, and yes, our imperfections. And as long as we can decode its cosmic whispers, Voyager reminds us that even the smallest signals from the farthest places can still all bring us home. Fixing a spacecraft nearly 24 billion kilometers away is never easy. Even when the solution seems simple, like asking Voyager 1 to start using the correct computer subsystem again, the process takes weeks, even months. In this case, it worked, but only after extensive simulations, careful command sequencing, and painstaking patience. By November 23, just as Voyager 1 was recovering, a new issue arose, this time with the Flight Data Subsystem, FDS. This component is responsible for formatting and transmitting science and engineering data back to Earth. Suddenly, Voyager 1 was no longer sending usable information. The spacecraft was talking, but speaking nonsense once again. It took until June 2024 for engineers to fully restore normal operations. That's nearly 7 months without good data. And yet, the team never gave up. With every line of legacy code, with every adjustment to the memory map of a 1970s computer system, they inched closer to a fix. But the real drama? That came with Voyager 2. In July 2023, a routine command was issued, just one of many daily transmissions. But this one had a minor error. It instructed the spacecraft to turn its antenna just 2 degrees away from Earth. Only 2 degrees. But across the immense gulf of interstellar space, that was enough to sever the connection entirely. NASA had no way to talk to Voyager 2. And worse, no confirmation that it could even hear anything. It was as if the spacecraft had simply vanished. What followed was one of the most intense, high-stakes engineering feats in deep space history. The team decided to shout into the void, using the Deep Space Network to broadcast a powerful wide-beam command, hoping Voyager 2 would catch it. Think of it like yelling across the Grand Canyon and hoping someone hears you through a pillow, wearing earmuffs with their back turned. And then, it worked. Voyager 2 responded. The engineers were able to reorient the antenna, re-establish the link, and resume operations. A miracle of coordination, physics, and sheer determination. These incidents are more than just technical glitches. They are reminders of how fragile our connection to these spacecraft really is. With every year, the RTG power levels decline. More systems are being shut down to conserve energy. Soon, the instruments will go silent, one by one. Eventually, even the carrier signal, the faint hum proving Voyager is still alive, will fade. And yet, as of today, both the Voyager 1 and Voyager 2 are still operational, still sending data from beyond the reach of sunlight, still contributing to science. Each glitch, each loss of signal, each painstaking fix is a victory for human ingenuity. But it's also emotional. These aren't just machines. After nearly 5 decades, they've become our shin companions in the void, our silent ambassadors, our longest-running experiment in interstellar exploration. They were launched before the internet, before cell phones, before GPS, and yet they continue to function. At the infinity beyond, we see in Voyager the whole resilience of the human spirit. A spacecraft that should have stopped working in the 1980s is still out there, reporting home. And the people behind it? Many have retired. Some have passed away. But new generations of engineers, scientists, and dreamers have taken their place, continuing the legacy. Voyager doesn't just teach us about space. It teaches us about ourselves, about persistence, problem-solving, and the audacity to reach for forever. So the next time a signal gets scrambled or an antenna drifts slightly out of alignment, remember that data traveled for over 22 hours through the silent dark across billions of kilometers just to reach us. That whisper from the stars? That's Voyager, still speaking, still flying, still reminding us that even the oldest technology, guided by the brightest minds, can accomplish the most extraordinary things. As we pull back from the stories of Voyager and its incredible odyssey, our gaze now shifts, not to spacecraft, but to the fabric of space itself. Consider the haunting beauty of a black hole, a gravitational monster so dense that even light cannot escape. When you observe an image of a black hole, like the now famous rendering of its glowing ring, you might notice something strange. The light appears to wrap around not just the equator, but also across the top and bottom. It gives the illusion that the black hole has rings on all sides, almost like Saturn in shadow. But here's the truth. Those aren't separate rings. What you're seeing is the same ray, bent by gravity. The immense gravitational field of the black hole warps space-time so drastically that light rays traveling upward or downward are curved back toward the observer. You're seeing both the front and back of the ring at the same time. This phenomenon, called gravitational lensing, is one of the most mind-bending and beautiful effects of Einstein's general relativity. And this brings us to a deeper question. What does gravity do to the shape of space itself? In a flat universe, everything follows straight lines. Space behaves like a calm ocean, predictable, linear, simple. But what if those lines bend? What if space itself is curved? In a positively curved universe, the lines of reality, light rays, gravitational paths, even time itself, begin to converge, like lines on a globe. Imagine trying to draw a straight path across a sphere. Eventually, every straight line bends inward. This suggests a closed universe, finite but unbounded, like the surface of a balloon. In contrast, a negatively curved universe stretches outward forever, expanding like a saddle into infinity. So, which one do we live in? That's still one of the great unsolved questions of cosmology. But missions like Voyager and telescopes like James Webb help us get closer to an answer. They gather data about cosmic background radiation, gravitational waves, and galaxy distribution. Data that helps map the geometry of the universe itself. It's humbling, isn't it? A spacecraft built in the 1970s, drifting alone in the dark, still contributes to our understanding of something as vast and philosophical as the shape of existence. That's the beauty of science. It begins with simple questions. Where are we going? What's out there? And it leads to profound truths about what we are made of, what reality is, and how the universe will end. At Infinity Beyond, we believe that stories like Voyager are more than historical footnotes. They are all living stories. They are still unfolding, still whispering. From the cold edges of our solar system, to the bending of light around a singularity, to the curvature of all space, every discovery, every signal, every faint photon caught in a telescope, it all speaks to one thing. We are part of something far greater, something elegant, mysterious, and waiting to be explored. So whether you're a scientist, a dreamer, a stargazer, or someone hearing this for the first time, let Voyager be your inspiration. Let it remind you that we came from dust, but we reach for the stars, and that somewhere out there, beyond gravity, beyond time, beyond even the pale blue dot, a spacecraft still drifts quietly, carrying the story of who we are, and maybe, just maybe, that story is still being written. As we gaze into the vastness of the cosmos, we often wonder, why is the universe expanding faster and faster? Some scientists attribute this to a mysterious force called dark energy, an unknown factor that counteracts gravity and pushes the universe apart. But what if there's another explanation? What if, instead of being driven by some invisible force, the universe is simply hyperbolic in shape? A kind of geometry where space naturally curves outward, creating a reality that expands itself. In a post-flat universe, space is infinite. If you travel 1 light year, you simply find 1 more light year's worth of space. But in a hyperbolic universe, something more dramatic happens. For every light year you travel, you uncover, say, more than just another light year of space. It's like stepping through 1 door and finding 2 new doors behind it. Then 4, then 8. Space unfolds exponentially in a cascade of endless possibility. That would mean the universe is not just infinite, it's more than infinite. The deeper you go, the more it gives. But this comes with a consequence. In such a hyperbolic universe, over enough time, everything beyond a certain distance would drift away, faster than light. Why? Eventually, the galaxies would disappear from view. Not because they moved too fast, but because space itself stretched too far. One day, our descendants could look up into the night sky and see nothing. Just stars of the Milky Way, suspended in a growing black silence. They might not even know other galaxies ever existed. And here's the twist. Despite this mind-bending concept, when scientists look across the cosmos, measuring light from galaxies billions of years in the past, they find something surprising. Everything still looks flat. The cosmic microwave background, the afterglow of the Big Bang, appears smooth and uniform. Galaxy distribution follows patterns that match a flat space model more closely than a hyperbolic one. So maybe our universe is flat after all. But even that doesn't close the book. Flat space can still be infinite. It can still support expansion. And it can still be filled with mysteries we haven't even begun to imagine. Whether the universe is flat, hyperbolic, or spherical, The key truth is this: it's full growing, and we're part of that story. We're observing it, measuring it, wondering about it. And thanks to spacecraft like Voyager and telescopes like James Webb, we're not just watching the universe grow, we're chasing it. Even if we never reach the edge, even if such a thing doesn't exist, the pursuit brings us closer to truth. Here at Infinity Beyond, we don't just ask how the universe expands. We ask what it means to be inside something infinite. To live in a reality where every discovery creates more questions, where every corner turned reveals another hallway, where infinity multiplies. It's humbling, terrifying, beautiful, and it's what makes space and science more than knowledge. It makes them a journey. So whether the universe is curved like a saddle, stretched like a flat sheet, or shaped like a cosmic balloon, there's only one direction left to go. Forward. Todd. Imagine you're observing galaxies at the edge of the observable universe. They're not just drifting due to cosmic expansion. Some of them are moving in the same direction, as if being pulled by an unseen force. But here's the catch. When we look in that direction, we see nothing. There are no visible clusters, no immense walls of galaxies, no supermassive attractors, just darkness. And yet something seems to be exerting a gravitational influence. Scientists call this mysterious phenomenon dark flow. It suggests there may be something outside the observable universe, perhaps a massive region of space, or even a parallel universe, exerting a gravitational pull on everything inside our cosmic horizon. Controversial? Absolutely, because this challenges one of the foundational assumptions of cosmology, that the universe is homogeneous and isotropic, the same in all directions, without special locations or flows. Dark flow throws that idea into question. The notion of a massive gravitational source beyond what we can see is hard to reconcile with general relativity. If space is expanding faster than light beyond a certain point, nothing, not even gravity, should be able to reach across that divide. So how could anything beyond the cosmic horizon affect us? There may be a loophole. While it's true that we can't receive new signals from regions expanding away faster than light, gravitational effects from the early universe, before that expansion kicked in, might still be baked into the motion of galaxies today. In other words, if a massive structure existed before inflation, its gravitational signature could still echo through the cosmos, influencing how large-scale structures move billions of years later. But if that's the case, then what is this structure? A gigantic supervoid? A cluster of primordial black holes? Or perhaps the edge of a multiverse collision zone? Some physicists speculate that dark flow might be evidence of other universes, brushing up against ours in the early moments of cosmic inflation, causing ripples in the gravitational field that continue to tug on matter today. If true, this would be the first indirect evidence of the multiverse. Others argue that dark flow is a hot measurement artifact, a misinterpretation of how the cosmic microwave background radiation behaves at massive scales. So far, the evidence is tantalizing but inconclusive. But here's what we know for sure. Something unexplained is happening, and in science, that's the most exciting place to be. On the edge of the known, staring into the unknown. At Infinity Beyond, we believe the purpose of science is not just to explain what we see, but to inspire us to explore what we haven't. Whether dark flow turns out to be a clue to new physics, a whisper from a neighboring universe, or just a cosmic coincidence, the act of searching is what defines us. Because every time we look deeper into the dark, we discover more about the light. Let this be your invitation to keep asking questions that don't have answers, to follow the galaxies where they drift, and to consider, if only for a moment, that there might be more, far more, beyond the visible edge of everything we've ever known. Maybe, just maybe, the universe is only the beginning.